Good afternoon and welcome to the Embedded Executive Podcast. I am Rich Nast. I am with Embedded Computing Design. My guest this week is Steve Tadeusian. He is the Senior Vice President of the IoT Compute and Wireless Business Unit at Infineon Technologies. How you doing, Steve?
I'm doing great. Thanks, Rich.
So I'm giving a gold star to myself because this is like the third or fourth time that you've been on the podcast, and it's the first time I've pronounced your name correctly.
Yeah, you did well. Thank you for that.
I get a pat on the back for that one. We've talked about lots of things in the past. Today, the topic is industrial power conversion. Because I know you guys are pretty active in that space. So just to set the baseline, what is your definition of industrial power conversion? What are we talking about here?
Well, we're talking about primarily, I think, with our newest products, AC-DC power conversion, but in addition to that, DC-DC conversion for different loads in a wide range of industrial systems. I think obviously the hottest market right now is around power supplies for AI cloud support. So it could be data centers, but in addition to that, we're talking about telecom, wide range of industrial applications for power supplies and UPS systems. And then if we look at photovoltaic, it could be microinverters or string inverters, could be your AC/DC charger in your garage, for example, for your electric vehicle as well. So a wide range of kind of use cases, but in the end, it's all about converting power that's coming from the wall into something useful by the end product.
And what is the level of power that we're referring to here?
So this is a great question because it's changing almost every day right now. So if we looked back maybe a couple of years in terms of like a data center, you might see a 2 kilowatt PSU in those systems. Today you might see a 5 kilowatt system, and what we see in design now are 8 and 12 kilowatt systems. So needless to say, and I think it's pretty prevalent in the news, those data centers can consume a lot of power or energy. And how do you minimize that is a big trend in the industry right now. So making those systems more efficient, operating at higher power levels, and converting that power in a more efficient way.
Okay, so I'm going to take this out to what used to be the extreme, which is now the norm. These data centers are consuming, I was going to say ridiculous amounts of power, but huge amounts of power. And it's at the point where it's a problem. And there are many states who are not welcoming these data centers just because they take too much power and they just don't know what to do with them. Are these real concerns? And is there some sort of solution on the near term?
Well, I think those are real concerns. And I think the solution here is to continue to work on system efficiency. And that's from the power generation all the way through the consumption in the data centers. What we are, well, I don't want to say as Infineon primarily focus on, because we support that entire chain from power generation to power consumption, and with a range of power devices and microcontrollers to manage those loads in the most efficient ways possible.
Is the solution to produce more power, or is it to reduce the need, if you know what I mean, have lower power consuming devices, or both?
I think it's going to be both.
Yeah. And is there just enough power to go around?
That I don't know. Like you're outside of my area of expertise there, Rich.
Okay. All right. So say we were having this conversation a year from now. What would we be doing? Is it just the same devices getting incrementally better, or is there something revolutionary on the horizon?
I think what we're seeing is already a pretty significant change is happening, I'll say right now in this field. And that is this conversion on the power side to wide bandgap power devices, like GaN and SiC, for example. And that is enabling much higher switching frequencies in these power supplies, which is driving up the overall system efficiency. Now, to control those devices, though, there's also a change that is happening real time right now in terms of the microcontrollers that are used to control those systems, because they need to support those higher switching frequencies in an efficient way and in a reliable way.
There's always a number where we say, okay, this is where you use silicon carbide and this is where you use GaN, and those numbers move a little bit, but they don't seem to be moving a lot. Do you see those numbers staying the same? Where, and I don't know off the top of my head what the actual numbers are, but it's like up to 400, you'd use silicon carbide, or I'm sorry, use GaN, and then above that, you'd use silicon carbide. Is that still sort of the rule of thumb?
I think so, but I think, as those technologies become more mature, I think you'll see more and more innovation in both of those areas that will broaden their applicability.
And is there some other chemistry out there that we should be looking at?
That's a great question, and I don't know the answer to that one, frankly.
Okay. Where is Infineon in all this? I'm sure you guys aren't sitting by the side and just watching what's happening, because you guys are one of the leaders.
Yeah, so this is a really fast-moving market, especially right now. And we look at this as an overall system. And we think that approach helps developers get their products to market faster in a fast-moving market. So we look at, again, on the power side, how do we bring industry-leading devices to help them get the best efficiency out of their systems? And then on the control side, how do we bring microcontrollers into this space that are able to deliver the capabilities to support those wide bandgap devices, for example? And it's not only about the hardware, of course, which I think is also, by the way, I'll just a side comment here. I think this is a really interesting space because in a lot of, okay, say, digital applications where my group focuses on the microcontroller side, it's mostly a software effort. And not to say that there's not a heavy software lift here, but the combination of the hardware and the software working together seamlessly is not only critical. This isn't about your PC rebooting or your doorbell having an extra, half a second of latency in it if there's a software glitch. This is about, really, frankly, potentially dangerous situations evolving if these systems from a hardware and software perspective aren't rock solid. So it's a unique developer, I think, that takes on these system solutions. The other piece of this then that we offer beyond the hardware are specific software tools. We have something called Power Suite to help developers rapidly configure their designs, as well as a set of power conversion libraries for various topologies to help them to move faster to market and deliver a robust, reliable product at the end.
So to be clear, these are software tools that are used in the design of the system, not while the system is functioning. We're not doing dynamic things, are we?
That's right. That's right. What we're providing is the software tools for developers to develop the system. What runs on the device, we do provide power conversion libraries and other, okay, call it like telemetry software around how the system is operating. At the end of the day, if there are things that the developer decides to monitor and adjust real time, that's in their application code, of course.
Okay. Infineon just had an announcement recently in this space. Can you go through that quickly?
Yeah, so what we're announcing is this new tool, Power Suite. So we have a set of new devices very specifically targeted at data centers and telecom PSUs, so that are adopting these wide bandgap devices. And those those microcontrollers then need the support in terms of the tool chain and configurators for developers. But it goes beyond that. Like I said, there's software libraries for power conversion for PFC, range of topologies, for LLC, half bridge, full bridge, for example. So what you would find in a power supply design. But in addition to that, there's a whole suite of visualization tools as well, so that developers can see what their change, or when they make changes, what the implications of that is real time as well during the development.
This is pretty interesting because back in the day when I was working on power systems, it was somewhat of a brute force, generally analog, and you just matched up the components and everything sort of worked as close as it needed to. Now you're into a completely different space where you're using software to design these systems. So has the role of that power engineer, this from the system side, the power engineer, has that changed dramatically? And is he more of a software guy? God forbid.
So it's happening. It's happening. There's still certainly experts, I'll say, on the say the more traditional or specific power design and hardware design. And this is where I was going earlier in terms of like it's really a dynamic system that both sides of it to get the most efficiency out of the system need to be understood and then tuned well. And I think what we are doing helps developers move out of a, I don't want to call it trial and error, but like you said, put things together, see how it works, maybe tweak the hardware a little bit this way or that way, change this component, see do I get something better. Move all of, or a lot of that tuning into the digital world because now you have digital control of the power conversion, and then be able to make those adjustments in more real time, but also bring in things like simulations into your code base as well that you've done in simulation tools for model-based design, for example. So I think to answer your question shortly, yeah, the role of the power engineer is changing. And I think for those that are going to get the most efficient designs at the end of the day are gonna be able to understand how to leverage these latest and greatest tools that the industry has for the software development aspect of it.
What's the learning curve for a tool like that?
So for our tool Power Suite, frankly speaking, the learning
Yeah.
curve is pretty low. It really is a configurator. So I think most configuration options in there, I would say a more traditional hardware-based power designer would recognize those things and be able to understand what they were configuring in the system. And that's really what one of the aspects we're trying to do is meet the designer or the developer where they are, and bring them into this other world as applicable. So they don't need to open up a terminal and start programming in C, for example, or open up Copilot and tell it what to program for them. They can make that transition from a traditional hardware design to one using digital control.
Boy, did you just open up a can of worms there. Uh, Maybe we'll save this for the next podcast, but
Sure.
do we even need the person to do that anymore? Just plug that stuff into AI and say, design this thing for me?
I think you still need the person. There's still a lot of other work to do other than the base code generation, at least for now.
I'm offering an invite to you to come back for another
For sure.
podcast and let's have that discussion because
Yeah,
boy,
I
is
think
that not only interesting, it's scary.
yeah. There's a lot of interesting stuff happening in that space right now, as I'm sure you're aware.
Yep. Thank you, Steve. This is very cool stuff.
Right. Great. Thanks, Rich.
And you're making power cool again.
Great.
That was Steve Tadiosian. He is the Senior Vice President of IoT Compute and Wireless Business Unit at Infineon Technologies. And I am Rich Nass with Embedded Computing Design.